You got chapter 9 for me? So as I mentioned on Wednesday, if I can't pool the variances, if I have to deal with those separately, I've got to adjust somewhere else. The adjustment I make is in which t-curve I use, and I choose my t-distribution based on the degrees of freedom. Now, this Welch's correction I apologize in advance. I'm going to calculate my degrees of freedom like this. You got to be kidding. First of all, I don't ever want to do this by hand. But what this does is it changes the degrees of freedom. And if it lowers them, it increases the odds that something in the outliers will occur. And if I have larger outliers, that basically gives me a bigger chance of having something happen out there. So this actually compensates for being unable to pool the variances. But I will tell you with 100% certainty, oh, hell no. I'm not doing this by hand ever. Unless, and this is a huge unless, all I have are the summary statistics. If I was given the means, the variances, and the counts, but not the raw data, Excel won't do this. Other statistics programs, Jamovi or MStat, that's the other one's name. I didn't write it down. But a lot of other statistical analysis programs will do this with summary data. But Excel won't. Excel will only work with the raw data to do these calculations. I believe on our Canvas page, I put a sample Excel sheet that does do this from summary data. I think it's in our examples, might be in our handouts. Oh, Jacob, there, TI statistical test, that's the manual for the Texas Crowd Instruments Calculator. Chapter 10, section 201. That's the one I built that works from summary information. It will do the calculations, but it's all done in the background, and we have to do them manually. So I basically did them once already. If you want, you can download that and continue to use it. But I think it's less useful because most of the time, we're not going to get the variances and the standard deviations except from the data. We're not going to get them given to us. Oh, and speaking of, I figured out where I went wrong on Wednesday. On Wednesday, I kept doing this problem. Nope, that's the wrong one. Give me the correct Excel sheet. Here we go. This was our upper and lower river issue. And I said, why is it coming up with 11, not 2.57? Well, the answer is because I typed something in wrong. When you do the data analysis test, for a z-test, 2 samples for means, I typed in something wrong. It wants the range for the first set of data and the range for the second set of data and then the difference. And the next 2 lines are where I screwed up. Because the next 2 thing it says is variance known, not standard deviation known. I typed in the standard deviation where I should have typed in variance. So I didn't square the numbers. I gave it a variance of 10 when the variance was 100. I gave it a variance of 15 when the variance was 225. So I was dividing by way the wrong numbers. My fault. When I fixed that, .57. There's the z-value I wanted. Whew. So it does work. We just have to type in the right stuff. Most of the time, I won't know whether or not I can pool the variances unless I'm explicitly told, or I know that the 2 samples are coming from the same population, which means more often than not, I'm actually using this version. But it turns out that this, when the variances are pooled, does actually give me the same answer. So really, if I know that I have a sufficiently large sample, I'm most likely going to use this unpaired idea. Question? Chapter 10. So really comes down to 3 questions. Are the populations skewed? Are there outliers? If the sample sizes are sufficiently large, do I use Z versus T? Then the one that we have to answer that isn't statistics driven, but interpretation driven. Is this important? Not just, is this significant? So there's a difference between the 2. And I need to know which one I'm going to do. So let's do one. Page 375, problem number 9. For a marketing class term project, Bob is investigating whether college seniors eat less frequently at a fast food chain than college freshmen. He asked 11 freshmen and 11 seniors to keep track of how many times they ate at a fast food restaurant during October. Assuming equal variances, there's the key. Can you conclude that this difference, the mean, is significantly smaller for seniors at 0.05 for an alpha?
You have to do a p-test for the C.
I got to do the whole thing.
Good.
But, oh, hold on. I want to do this in Excel so I can show it to everybody that will use that technology more often. But I'm going to do a t-test because I only have a small number. I don't have known variances, and it says I can assume they're equal. So that's a t-test, assuming equal variances. I need this raw data. It's in the file labeled fast food. So I need to go download that file from our Canvas page or pull it up where I already have it. There it is. Fast food example. Data. Okay. If I'm going to let Excel do the work, then the thing I need to be able to do is interpret the work it does. So, under the Data tab, Data Analysis, t-test to sample, assuming equal variance. Variables 1, seniors, because it's on the left. It doesn't matter which one you call 1 and 2. Variables 2, make sure they're the same size in this case, because they are. Yes, I have labels. My hypothesized mean difference is 0. I don't know if they're different at all, but I want to know if the difference is anything. But wait a minute. In the question, what did they ask? Can I conclude that the mean is significantly smaller for seniors? Seniors was my population 1. So the hypothesis I'm doing is that mean 1 less than mean 2. That's my alternate hypothesis. It's a one-tail test, not a two-tail test. So alpha is 0.05. Let's put my stuff in a new sheet. Okay. It did all the work. I need to answer the question. And that means that the physically hardest, well, mentally hardest part of this entire problem is the stuff we already did, figuring out what our hypotheses were, then knowing what piece of information here matters. So, at alpha equals 0.05, do I accept the null hypothesis? There's no difference between the groups? Well, the average for the seniors is not smaller than the average for the freshmen. Or do I reject it? There are 3 different useful numbers here.
We reject
Because
because the stat is bigger than T3.
what we call the t-calculate is what Excel calls t-stat. They just changed this is the statistic t rather than the calculated t. And then the critical one for a one tail is right here. And if the absolute value of the statistic is bigger than the absolute value of the critical, 1.8 is bigger than 1.7, I reject. What's the other way I could have come up with that same answer all of a sudden?
We can check if the p-value is bigger than alpha. The smaller.
The other way around, smaller. I want to be in the rejection zone, and that means that the p-value needs to be smaller than the section I'm rejecting. The section I'm rejecting is 5%. The chance that we got this result randomly is 4%. Notice I have to use the one-tail stuff. Because if I used a two-tail test at alpha equals 0.05, I would not reject. Because the p-value is 0.08. So which test I use matters. If all I was asking is, are they different? And the answer would be no. At 5% sensitivity. But I was specifically asking, is the mean for seniors smaller than the mean for freshmen? In this case, the answer is yes. What if I change this from equal variance to unequal variance? Because I don't know that there's any reason to assume equal variances. You? There's nothing here that population of college students. Why would the variance among freshmen be the same as the variance among seniors? Don't you think people's behavior changes over 4 years? What you do at 18 and what you do at 22 is usually pretty different. Oh. But if I want to know what happens when I don't have equal variances, I have to do the other test. I have to use the different PF. I have to use the different calculation. I have to click one different button. Let's go back to the data. Data analysis. It's the very next line. T-test, two-sample, assuming unequal variance. I literally don't have to do anything different except right here. Everything else stays the same. Tell me where variable 1 is. Tell me where variable 2 is. What's the difference that you're assuming they have? Did you highlight the labels? And what's alpha? Everything in this box is exactly the same, whether I'm doing equal variance or unequal variance. All the calculation changes happen behind the scenes. Variable 1, oops, click. Seniors. Variable 2, freshmen. Hypothesized difference, 0. Yes, I clicked on the labels. Yes, I want it in a new sheet. Go. Same question. Do I reject or support my null hypothesis based on the statement? Again, I look at the p-value for the one tail, it's 0.04, I reject. Is there a difference between the values for the one tail and the two tail? I'm sorry, for the equal variance and the unequal variance. This is the unequal variance. This is the equal variance, 04244, 04284. Oh. Teeny weeny little difference, right? The groups were the same size. There weren't very many in each group. And apparently the variances, if they're different, they're not a lot different. Yes, sir.
Like, oftentimes whenever we're like doing on a test, we would round to like 2 to 3 decimals. So does it even make much of a difference?
In this case, no, it doesn't. I can't guarantee that all the time. And that's where, in particular, especially with groups of very disparate size, like with our river example, where one group was 10 and the other was 15, that's a bigger difference. These groups were both 11.
Mm-hmm.
When the group disparity is larger, well, group size disparity is larger, that's where I'm going to run into a chance that the variances are more substantially different. And since variance is squared, any small difference gets exaggerated. I find it safer to assume unequal variances. If I'm doing the test just for me, that'd be the test I run. Now, Leo, you said I can do this on the
We
calculator.
could do like the list, you put your L1 and L2, because one could be seniors and one would be freshmen first.
Exactly. If I take this same set of data I can put it in my lists. Edit my lists, put those in there. And then stat tests to sample t-test. Now, this is the one where I give it the summary data. Excel won't do summary data, but the calculator will. Way down here, the way I tell it whether I'm assuming equal variance or not is whether or not I get to pool the variances. I can only pool when I assume equal variance. That's the statement there. So this, as highlighted, would test for equal variance. If I want to actually give it the lists instead, I need to tell it where the list is. But again, that same option is still there. Do I do this as equal variances or unequal variances? Question. Yes, sir.
So say we're assuming something is equal variance and we do unequal variance. Like on the calculator, I would say
Pooled no as opposed
Yeah.
to pooled yes.
Yeah.
Well, most of the time, if I am working with pooled variances and the population sizes are roughly equal, then the pooled variance and the unpooled variance are actually going to be very close. Especially if the population sizes are equal, then the pooled variance is the same as the unpooled variance. It matches out. But that's the exception, not the rule. My default is to go to unpooled variance. But if it says you should use pooled, your p-value is going to be slightly different. Your t-calc is going to be slightly different. But if you pool the variances, you should get a slightly smaller p-value, which is beneficial because that means you are making it harder to reject most of the time. Better?
Yeah.
Again, my default is to go to, oh, I'd rather do this as unequal variance. That way I don't have to assume. Now, I will tell you, equal variances are certainly simpler because the calculation is easier. Degrees of freedom is easier. But it's one button check difference. And if I'm not doing the actual by hand math, I'm going to not care. More questions? So, in the example we just did, we said the average number of times that a senior goes out to a fast food restaurant is 10.6. The average time a freshman goes out is 14.1. So the difference is 3.5, right? And that's statistically significant. The average freshman eats at a fast food restaurant 3.5 more times than a senior during October, based on the data we collect. I have a point estimate, 3.5. The difference is 3.5. I have a point estimate, usually want a margin of error. That's a confidence interval. I need to be able to get confidence intervals here, just like I got confidence intervals in T and Z before. I had a mean. I got a confidence interval for that mean. I have a mean difference. What's my confidence interval for the mean difference? Well, it turns out that I can construct a confidence interval exactly the same way. Again, what my choice is going to matter is which one I'm using. I'm gonna skip the Z version here because that means I have to know the population variance, and that almost never happens in real life. So I'm gonna assume we're dealing with a t-score here. And then the question is, am I pooling the variance or not? Do I assume they're equal or not? So if I know that the variances, if I assume the variances are equal, then I'm gonna do the same thing I did for a confidence interval. Of size 1 minus alpha. Remember, if we were doing a 95% confidence interval, then my alpha was 5%. If I'm doing a 90% confidence interval, then my alpha is 10%. Okay. 1 minus alpha. I'm going to need the right t-value. The t-value is t alpha over 2. I need t alpha over 2. And I'm going to use the degrees of freedom that we know before. So that's how I get the t-value I'm going to use. I go to the right t table of critical values, and I pick the number for the degrees of freedom. Everything that comes after this point is based on my standard error. But the standard error for a t-test is ugly. What the hell? All right, wait a minute. Let me go back to chapter 8 for a moment. Chapter 8, we did confidence intervals for the averages, for the means, for 1. Here, what the hell is this? Because I know I've seen that before. I'm having the weirdest sense of deja vu. I've seen this crap somewhere.
Stupid.
That's this number on the bottom. Yes, that's our degrees of freedom. This whole expression in the square root, this first square root thing, I've seen this before. On Wednesday. That's our SP. So that makes this the expression Because I take the square root, right? Variance is squared. This is SP. Now, somebody go back to the formula sheet you are writing for the next exam that contains formulas from chapter 8, chapter 9, and chapter 10, that you've already started to work on what formulas you have from chapter 8 and 9, right? That's the hint dropping. Find me the formula from chapter 8 for a confidence interval using a t-test. If you've got your book, you can just go to the end of chapter 8 where all the formulas are. Take a look there. Leo?
Is it next part plus or minus T of alpha over two times S over root n times large n minus small n over large n minus one in the square root?
That's for the finite population correction factor,
It would be the one up.
but it's the one up top here. And if I look carefully, T alpha over 2 times S, and then the square root of n is on the bottom, isn't it?
Over 0.95, why just do 0.025 instead? Because the alpha over two.
Yes. But look at this formula. T alpha over 2 times the variance, and then the square root of n is in the bottom. Only there were two n's, so I have to combine them this time. I'm using the pooled variance, and I'm dividing by n. This is the same formula, tweaked to work with two samples instead of one. The margin of error idea is the same, whether I'm dealing with one sample or two samples. Hot damn. The reason I point this out to you is that I hate sifting through which freaking formula do I have to use. But remember, it's really the same formula. Standard deviation times 1 over n. But I've got two n's this time. Okay, that's great. How's this going to change if I can't assume equal variance? I'm still going to need T alpha over 2 the same way. But if I'm using unequal variances, what changes? That was just over 30 minutes ago. What changes is that ugly DF. I can't use this degrees of freedom anymore. I got to use the ugly version. But then when I have it, I can do something simpler. I'll take the difference in the means. I'll use T alpha over 2 here. And then I'll use the nice version for the standard deviation. So this part gets easier. It's the DF that got harder. Again, I will point out to you that we get all these numbers out of the t-test itself. Here's our fast food example with unequal variances. This is the unequal variance version. We did this with alpha equals 0.05, right? That means the two-tailed t-value is with 0.025. There's T alpha over 2, right there, sitting in front of us. There. And the two variances. I can get the variances because they're right up there at the top, aren't they? S1 squared, S2 squared. 24.2 and 15.7. I can build the confidence interval right from here. Okay, wait a minute. I need the difference. X1 minus X2, right? 3.5. That was our difference in averages. Let me do the margin of error. So the margin of error is T alpha over 2 times what? Times the square root of variance 1 divided by count 1 plus variance 2 divided by count 2. And then I add or subtract that to my difference to get the confidence interval. Escape. CI low is this number minus my margin of error. Confidence interval high is this number plus my margin of error. Now, here's how close this decision was. When we looked at a one-tailed test, we said, yes, this makes a difference, doesn't it? I think that means I'm using the wrong margin of error number. I think I should be using, no, that's for two-tail. It should be this one. That's a bigger number, right? Because it's further out because the area got smaller. We said, yes, we should reject this. But in a two-tailed test, we said, no, we shouldn't. Look at the confidence interval. What do you notice about our confidence interval? Confidence interval contains 0. We go from negative 7.9, 7.4 to positive 0.5. 0 is in that interval, isn't it? A 95% confidence interval contains the idea that there is no difference between these two. And in a two-tailed test, that means I would reject, yes? If 0 is in my confidence interval, I should, for a two-tailed test, reject. For a one-tailed test, it isn't quite as clear. Notice if I switch to the equal variance version, that T critical two-tail is only a little bit smaller. It's still pretty close, isn't it? So that's still going to contain 0. And that's why in a two-tail test here, we would have rejected. Sorry, we would have not rejected. 0.08 is bigger than 0.05. Confidence intervals are most closely associated to two-tail tests. But I have all the numbers to build what I want here. Two sample T interval. Whether or not I do equal variances or not, there's my pooled question again. I can do this here exactly the same way. Whether I give it the data or the statistics. Question. Okay. Please notice we can also look at the two individual confidence intervals. I can look at the confidence interval for the first average, the confidence interval for the second average, yes? If those intervals overlap, I should make the same comment. That statistically, for a two-tailed test, they don't differ. Because the two intervals overlap each other, they have stuff in common, there's a chance they'll actually be the same. No difference. And that's what we're measuring here. We're measuring the difference between these populations. Question. Okay. The example we just did was freshmen versus seniors. But most of the time that I'm doing experimental work, gathering statistical information from things I want to compare to each other, I'm usually comparing versions of the same thing. So let's do a nice straightforward example. To quote Dr. L, increased exercise levels on average lower blood glucose. The more frequent short exercise bursts you do, 20 to 40 minutes, the more likely you will to have lower average blood glucose levels fasting. This is something to tell everybody who's diabetic, hey, you should get more exercise because this is what it's going to do to your blood sugar. I'm so happy to know this. I keep sticking my fingers every morning. It doesn't always help, but it's good to know. So I get a group of diabetics and I say, hey, how many of you are in an exercise program? And none of their hands go up. Great. Let's do your fasting blood sugars for a couple of days. We'll get maybe 10 samples. And then I'll get an average for each person, and then I'll go have them exercise for another month. and I'll test them afterwards. A before and after, right? I've got the same people, beginning and the end. Not different groups, the same groups. And what's more, if you're a diabetic, your blood sugar on fasting in the morning is different than mine. So does it make sense for me to compare my morning level before the exercise programs to your morning level after the exercise program? Make far more sense to compare me with. If I'm comparing one version of a product to another, product A versus product B, I go and I get a bunch of people and I ask their opinions of the first product. I ask their opinions of the second product. It's the same people. I should compare their opinion with themselves, as opposed to this whole group with that whole group. The stuff we were just doing took average of group 1 and compared it to average of group 2. I don't want to do that. I want to compare the individual in group 1 with themselves in group 2. I want to think of each individual person, each individual response as one of the values in my data set xi. So the x1s come from the before, and the x2s come from the after. And then I'm going to create a difference for each individual person. That converts all of the pairs of samples into single data points. Oh, wait a second. I no longer have two groups. I just have one group. I have the group of differences. And then I can do a one sample test on the D's. So I can get the average difference and the standard deviation for the difference. And I can say, oh, I've got a benchmark, right? So I said it earlier that exercise will lower your blood sugar level. Well, let's say it'll lower it by 15 points. I would then have a benchmark, 15 points. A 15-point difference. I'm going to call that mu D. Like, remember we called it mu 0 for our benchmark in a one sample test? But now this is specific to the differences. So I'm going to call it mu D. But this is a one sample set of data. So I use df equals n minus 1. Where n is the number of paired samples. And then I'm back to doing the same t calculation I did before. We'll look at some paired test examples on Monday. I hope you all have a wonderful weekend. I will see you then.